Hello and welcome back to Compiler Programming. In the episode before last, I implemented this startup functionality which allows me to specify a function that will be called when the program is just beginning to run before the main function is executed. And one of the reasons I wanted to have this functionality is actually for something else that is currently missing, and that is support for relocations. Relocations are a bit of an interesting concept, and to best explain what they are and why they are necessary, let me show you this piece of code. Let's say I have something like this global buffer, and that global buffer is going to be what should it be? Let's say let's not even do the buffer. Let's just do a simple character. So some global, and that is 0, not even a character, just an integer. And now I want to have a pointer to that global. So I will do some global pointer, and that is ampersand some global. This seems like a pretty reasonable code. You can write equivalent of it in C as well. It will work just fine. However, the way that it works is a bit interesting. If I open up Compiler Explorer, and I can do this stuff, and let's create this int main whatever return 0, and let's just say that we are going to convert to integer this global pointer, and we of course need to create that global pointer. Some global is 0, and int star some global pointer is ampersand some global. Right, what are you unhappy about? I'm missing a semicolon. That's fine. Okay, now we can look at the assembly, and it is kind of interesting. So what it says here that we have this data segment, and in a data segment we have a quad, which is a 64-bit value, which is the size of the pointer, that is pointing to some global. But how does it actually work internally? I think I can click this compile. Okay, I can do it in this codeball. So let's switch to the one that is with GCC, and that should help. And compile to binary. Can I run that? Yes, that seems pretty reasonable. So you can see there is this TL relocate static PIE. And what this thing does is it will make sure that we actually have the address here. So it works the same as the startup code, where before the main starts, there is a little piece of the program that takes this variable, this global variable, and adjusts its address such that it is correctly pointing to here. Now, it doesn't actually take the address. So if here instead I would do something like this, startup And I will say that some global pointer is this. So it is not exactly the same thing as what happens in C. So executable formats, including P32 that we support ourselves, and things like ELF and Mac-O for macOS, they have an explicit support for relocations. And instead of doing this exact operation, what the operating system does is it's two parts. So the C compiler, when it has global variables, it assumes that they are going to be loaded at specific address. I think in case of position independent code, and PIE stands here exactly for that. So PIE is position independent executable, I think. You basically assume that you're going to be loaded at address 0, and every global value is some offset from 0. So I don't know, it will be 1, 2, 3, whatever. And I believe that this offset is this variable. I'm not sure, but that might be correct. Although actually now that I'm looking at it, it is also possible that it is this one. So with ELF executables, it's a bit different because ELF executables actually do support loading at specific addresses, but Windows 1, P32, they do not. Anyhow, global variables are essentially just offsets in the data section of the program. And this relocation setup, what it does is it adjusts the starting address. So instead of assuming that it's 0, when the program actually starts up, we know what address it starts up on, and it adds that address to all the variables. So the code is not exactly the same as what happens between these two cases, but the result is actually exactly the same. So if we manage to do this stuff, then it will be exactly what we want. And to show you a bit more, let me actually do the following. So if we get pepper and we load this executable, then in sections, there is this .relog section. And if we go to relocation directory, there are two entries here. And this is what it says, right? So the variable is global, and it is 10 bytes or 16 bytes offset from the start of the data segment. And then when the loader knows which address the executable is going to be running on, it will just take this, apply this 16, and it will be correct. I do not want to implement relocations that way. And the reason I don't want to do it is because the executable format is pretty terrible, especially in this section. So there is legacy version of relocations that are only like if you have some amount of relocation and it fits into the legacy version, then you can use that. If you have more relocations than that, then you have to create a second section that is using slightly different setup. So it's a bit of a nightmare. And so far, I don't really see a good reason why would I do that. So why would I rely on operating system to do this patching for me where I can actually do it myself? There is a small thing about that. Like if I want to do the patching, the section of the code where patches reside has to be writable, but it only has to be writable during the patching, and then nothing stops me sort of from calling virtual protect, which we call in many places in our code anyway, and there is nothing really to it. You can just do it. So yeah, I think I'm just gonna not go the route of putting this in the P32 executable and instead try to implement it myself. we have all the base set up. And in fact, if I wanted for the code to stay minimal, I could just keep it as is. So this stuff should actually work. But would be nice if just by doing this, it would automatically do this stuff, sort of. So yeah, that is the plan. Let's see how we can do it. And we also need to figure out a good way to test this. And I think how we can approach this. I guess what I could do is I could change the FizzBuzz example. Well, let's create a new one. Let's create a new example. This would be relocations. And relocations is going to be the following. We can actually copy hello world as this slightly smaller. Startup code, right. I don't need any of this, none of that. Right. How do I want to structure this? So I think the easiest thing that we can do to make sure that this works is to have a one character string. So we would say like one, and here is a global string. Is a global char. So we get it like this, and then we say global char. I think that's not the syntax I support just now, so something like this. Cast S8. Actually, this should be U8. And we would say 32, I think. Let's check if this will work. A.bytes.0. So ideally, this should give me character A. This is also an interesting test for this whole thing. If it doesn't work, I will not go too deep into that, but it would be interesting if it does. Okay, so we have global char, we have global string, which is a pointer to global char. And the size of this string should be exactly 1. The type of this variable should be pointer to U8, which is what we have there. So this code should work, but right now it will not. Let's get it to... I actually want to split it into two parts. We will add a test function. And the reason I want to add a test function is because I also want to be able to run this as a JIT code. Because we have two parts, right? We want to make sure that executables work, and we also want to make sure that the JIT code works. Okay. Test. Right. And we can actually start with the JIT code because it is slightly easier to iterate. But before any of that happens, we have these complex examples. Actually, let's take the hello world. I probably need to refactor this stuff. There's lots of repetition here, but that's okay for now, I think. FizzBuzz. No, I actually do want the copy of FizzBuzz. Should be able to run code that contains relocations. Pictures, relocations. Just gonna call this module Module. We are looking for test, 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 test. Right. Something like that. Let's try to run this and see what's going to happen. Right. We get the error trying to access a runtime variable, a global char, from a different epoch. This is not exactly what I thought would happen. Interesting. Because I would expect global char to be the same one. Well, let's try to see what happens. First of all, there is a typo, different. And another thing, with epoch. Actually, we don't need this. Percent LU. Now it's percent pre U64 from different epoch. And I need to say percent pre U64. Right. This is good. Now we just need to provide these epochs. Context epoch, value epoch. Right, so first goes the value, and then goes the context. Does this build? Okay, this builds. We can now at least see the numbers. Okay, that is quite a number. So global char is 0, and we are trying to access it from epoch 155. I thought that this is okay. Let me recheck the logic here. Okay, we look up, there is no thing. Then we check if this is not a static value. Maybe a better option would be to also say explicitly that this is not a zeros epoch. Is this correct? Let's try to patch this like this for now, and then we'll see if that is actually what we want. Okay, now we have a to-do. Let's look at that to-do and see what happens there. Okay, so this is inside of our compile time execution. And the reason this is inside of our compile time execution is because we yeah, so this, it tries to evaluate this expression as a compile time expression, and it receives back a pointer and has no idea what to do with that pointer. Right. Interesting. So this is not exactly the problem that I'm trying to solve, but we need to figure out how this is going to work. I think we can allow this to just fall through, maybe, and then deal with it there. So let's try to just disable this check, because we have to deal with pointers to static values anyway in the assign, and this is where things will continue, I think. Right. So this printing means that we weren't able to find a variable somewhere, I think. Let's try to figure out where that actually happened. And for that, I will launch the debugger, and then we'll go from there. Okay. Does it actually crash, or are we okay there? Okay, so we are actually crashing, but I guess that's fine. Where is this happening? Handle function call, std out handle. Right, so this actually has nothing to do with the code at hand. It was crashing here. Okay, so it is kind of, the program kind of works in the sense that it prints something. You have this letter H, but letter H is definitely not letter A. And just to make sure that this works, let's actually replace it with the proper thing. Char code at 0, so we have 97. Okay, so we have 97. Now we definitely know that this should be A. Okay. So let's rerun tests again to make sure that it wasn't the problem of interesting. So now we again have a problem. What is this time? So when you find variable global string, it's really unhappy with this thing, I guess. So our cast is also not working. Right. Okay, let's just assume that this works, and then we'll go from there, because we still haven't implemented the actual relocation. Now we have this ampersand global char, and we need to figure out what would be the right way to realize first that we actually have a global that we need to point to, and then stash it somewhere in our code, and then do the relocations. I will actually start from the end, where we'll need to store the relocations anyway, and we'll need to stash them somewhere. The question is, how do we store them? Well, we need to know where to patch to and where to patch from. So like we need to know the location where the address will be held, and we need to know address of what are we taking. That means that we will need something like relocation as a struct, and here will be storage target. It's kind of ambiguous. Patch at, and address of something like this, I guess. Now we need to define an array of those. So do that, and we also need to create an array here. So array relocation relocations. We need to add it to our initializers as well. Array relocation relocations. Okay, that seems fine, and we also need to destroy it. Okay, that's that build. I can even try to run it again, just to verify that our array setup is fine. Okay, that seems perfectly okay. So now we have a place to stash this. Let's get back to trying to figure out that that actually happens. Okay, so here we receive a pointer as the result from the compile time execution. What do we need to know about that pointer to make sure that it is fine for us to even do that? Okay. Global string, global char. I'm just trying to figure out at which point do we need to put values into our relocation array. Is it at the point where we are assigning this thing, or at the point that we are creating this pointer? And it looks to me like I will actually have to change how pointers work, or how pointers are stored internally. Because in here, I need to know which variable I'm pointing to. Like in here, I will know the location only when I do the assignment. But in order to do the assignment, I need to evaluate this part of the expression, or this part of the assignment. And by the time we get to the actual assignment, I would have lost the name of the name, but like the value that I'm trying to get the pointer to. So I have nothing to do when I get to here. I know it's a bit of a mouthful, but let me try to go through the code and maybe it will be a bit more straightforward what is happening. First, we will go to our type generation where the value is defined, and we will go from there. So value, right? Actually, I don't want value, I want storage maybe, or descriptor. Right, so we have descriptor here. And as unfortunate as it is, we will have to have another field in here that will say unimaginatively we called value, or maybe value, and essentially this will allow us to track what value are we pointing to. And this is now required for relocation, but we also should be able to use this information for optimization later. Like if we already know what we are pointing to, and for example, what we are pointing to is known to be static, then rather than generating some runtime code, we could be just directly go into here. The reason I'm saying this is unfortunate is because now we have a value whose type includes a pointer to another value, which is slightly awkward to think about, but we sort of have the same thing in functions anyway, so it is what it is. Okay. Now I need to, let me think for a second. I need to record this, I guess, when we have address of, right? Okay, load address. So this is what happens when you do ampersand. We are loading the address of the variable, and right. So this is where things get interesting. And we need to do some checking. So if context builder, so this is runtime. Else, this is compile time. And at runtime, we can just do this. It makes all the sense in the world, and this is okay. At compile time, though, ooh, I just thought of something. Maybe I'm not sure I want to go there just yet. I need to think more about this. But what I was thinking is maybe it would be cool if basically any runtime evaluation that happens as if it should be done at compile time would instead be dropped into the startup code. I need to think about that, but for now, let's just keep it as is and go from here. So at runtime, we just load the res. What do we do at compile time? At compile time, actually no. The problem is we will have a builder, right? We will have a builder. Let me go to compile time eval, and I guess I will need to figure out what is the best way to detect that we are currently doing compile time evaluation. So JIT, context. Okay, so I guess that's one way. We could just check which program is currently active. Fine. So if context compilation JIT program is context program, so now this will be compile time, and the other one will be a runtime. Okay, so we do know that this happens compile time. Let's verify that we are getting here. We'll say to do implement runtime ampersand. Okay, if we're on the test, I expect this panic to happen. I just want to verify that we did the condition correctly. Yeah, we did. We are getting to where we are supposed to be getting to. So that's good. Now all that is left is figure out what is supposed to be happening here. Here we need to figure out if the value that we are trying to point to is as a global value. Whenever I interact with compile time execution code, my brain always wants to explode because it's very hard to mentally visualize something happening at compile time at the same it is being executed. So yeah, let's just say that we need to create a value. So result value, okay, value star pointer is value make. So first of all, descriptor star pointer, let's just go with descriptor, and that would be descriptor pointer to, and there is a context allocator and pointer. Right, we need to get this value out. Value star pointy. Pointy descriptor. Here we provide context, then we provide descriptor, and now we need to provide the storage. Right, so this is where we need to allocate some space in the global. No, this is not the point where we want to allocate space in a global array. Not at all. This is tricky. This is very, very tricky. Okay, so let's just power through this. For now, I'll put here an empty storage and then think about it as we go further. So we have empty storage, and then we need source range, which is pointy source range. Okay. Now we are going to assign this pointer to the result value, something along these lines. But I feel like I will also need to check for this epoch. So let's just do assert pointy epoch is 0. Is my assumption correct in this case? It is not. And the reason it is not is why exactly? Global char should have 0 epoch, I guess. Right. The problem is we need to force the value first. Okay. I guess then array get args. Yeah. So here this is fine, I guess. Although I'm now not entirely sure. Oh, this also was a bit icky. Okay. Okay. You did magical argument, so it should be forced. Okay. Then why that is not the case? That is not the case because token match call argument creates a new value. I think that is why. Yeah. So it does this jazz, which is kind of unfortunate, which means that. Wait. Are we not copying the epoch when we are assigning to an any? Right. So that is what is going on here. We should be copying the epoch when we are assigning to an any value because it is just a placeholder. And let's try this again. Okay, so that is actually progress. And now we are failing. I think I even know when. This is compiled execution. It is not happy, right? Or not? Um, 4, 5, 6, 5. No, it is actually the it's a variable definition that is unhappy. But how did we even get there? Compile time eval. I would expect temp result storage. So we get back a pointer. So I would expect us to get here. And then we create a storage that is static. So we should get to here. And then we assign temp result to result value. What is going on? Okay. What we're going to do is we are going to focus this test. Then we're gonna go to compile time eval, and we are going to add breakpoint here, and then we're also going to go to that address of code and get the breakpoint in here. Okay, let's see what's going on. I believe that this is not actually the one that we are interested in. Result. Oh. Yeah. So this value is actually the global char. So this is fine. There is nothing interesting here. Now we get to that ampersand global char. Let's see what's going to happen here. We go to here. We get descriptor. Descriptor should be a pointer to char. Let's verify that while we are at it. This is a pointer. Yeah, it is a pointer to char. That is perfectly fine. We create a value. We do assignment. What is our result value? We should define operator, parse expression. Okay. Oh, interesting. Interesting. Right. So what is happening is that we have a shortcut code that's very important for the system to function, and that is here. That basically checks that if while we are doing a compile time evaluation of an expression, we have not generated any actual instructions, so everything was resolved during parsing, then there is no point in running code because there is nothing there. And we can just return this directly. But here we probably need to verify that. So something like this, assert storage. Do we need to assert that storage is something specific here? Guess maybe not. I'll just mark this as a point of interest, and then let's think more about it. Anyhow, the point is this thing now propagates all the way to here, to the actual assignment, and we need to figure out what to do about this value. I think I need to look at the assignment code and check what happens here. So when we define a global variable, we do compile time evaluation of expression on the right, then we do some checking for immediate integers, that's fine. And then we check that the storage is labeled. So what we could do is when we are doing this ampersand address of stuff, so right here, when we do this code, we could create a new global value and return that. That should work, probably, for this specific case. And then we can go from there. Okay. So I think I have code for this in the assignment. Yeah, allocating section memory, blah, blah, blah. Yeah, that seems like what we want. We don't really need to mem copy anything, I guess. What are we doing at startup code? Startup, right? And that's fine. And what about here? Okay, yeah, so looks like we'll need to clean up this code. But for now, I'm just gonna again copy that. And then I will clean it up later. Okay. This needs to be in RV data. I think later on I will create a separate section for it. As I said, because we will need to flip the permissions. When we just loading the program, it needs to be read-write so we can do the patches. And then after the program has finished initializing, we should make it a read-only. But that is a separate. I can do a to-do. Put this into a separate section and make read only after relocations are done. Okay, byte size. The size of it will be a pointer. Alignment is pointer. Label index. Byte size. Okay, that makes sense. Global value. That's okay. Descriptor. That's fine. And that's also fine, I guess. We don't need to do any mem copy, so we just leave it initialized. In reality, this should actually, this section can probably be 0 initialized. So there is this special thing in executables where you can mark a section that is initialized as 0. That way it doesn't take any space in the executable, but is mapped into memory. Okay. So I guess that is what we want. If I'm understanding this right, what should happen now is we go through this code, we create that global value. We will get all the way to here. We will check that the storage for this thing is a label. We will go into this case and we will just define it correctly. That is the hope. We still are not actually doing the relocations, but we should stop crashing ideally if I did everything right. No. And the problem here, the problem is again with epochs. I need to think about it. For now, I'll just say to do should be a better way. Okay, we get a different symbol, but that's perfectly fine. We basically are just now reading arbitrary memory that just happened, whatever happens to be in there. It's obviously not great, but that it is what it is. Right. Now the relocation part. We can do what? We can say that dynamic array push context program. Is that right? That's actually not right. And we cannot do it here because we have the wrong program. This is a compile time execution and we are interested in runtime. And right now I don't think I have a way to always get to the runtime program, which is, oh no, I actually do. Okay, so then we can do it here. Context, compilation, a runtime program, and that is gonna be then relocations. And what did we call all of that? Relocations, relocation patch n and address of, okay. So patch at, that is the location of this pointer. So let me do storage pointer storage, right? Goes into here, and it also goes into here. And here we will say address of, and we would say point t storage. And I also want to check that assert pointee storage tag is not storage tag static. We want memory, basically. We can even assert that. We always want memory here. Maybe that should be an error, not an assertion, but for now, I'm okay with an assertion. Okay, so we pushed this stuff to here. Let's verify again that this does not crash. It doesn't. Now we should be ready to do something about that. Win32 platform, no. Win32 runtime. Startup, relocations. This is part of incremental setup. Every time we call a JIT, we remember how many things we already processed and not process things that we don't have to. Okay. Call new startup functions and right. And resolve relocations. It's an interesting question whether we should just shove somehow relocations into a startup function right away. I think for now I will do it this way, and then I will think if I want to merge these two. Probably should, because it is why I created the startup function in the first place, but let me first get all of this to work. Relocations, because the thing is, if we merge them, then we would have a problem with making this incremental, right? So actually for JIT, I will have to keep it separate, but for P32 here, I could merge them. I think that's okay. Locations, relocation count, info relocations, previous counts, relocations, relocation count. Okay, that is great. And now what do we do? Well, we get the relocation from here and we do the patching. How does the patching work? That is a bit tricky. We need to look at what happens here, right? So we need to say that assert storage is label of relocation address of. You need to make sure that both of them are labels. And patch at. If they are labels, then I think there is a nicer function to deal with that. Yeah, we can. No, that's actually. Right. Okay. Label. Okay, so we want this. Label index patch at index is this. Okay. And then we have address of index. This is this. We have address of is address of index, and here we have patch at, which is patch at index, but this is actually S64, and now we can say patch at is S64 of address of. Right. So again, what we're doing is we have two locations in memory, and we are taking the address of one of those locations and putting that address into another location. Something like that. Does this build? No, not at all. Storage is Lamo. That's just the problem of adding these to here. Okay, those are not pointers. Right. We need to also add this function to here. And we are good. Well, this is sort of the moment of truth. If I did everything right, then we should see what we expect, but let's see. Well, apparently instead we crash. Or go on in forever. One of those two. Well, let's go here and I want let's see what happens. So we get to this array. Relocation count is 1. That is perfectly fine. We have our patches. So what are our relocations? They both memory, they both labels, everything is great. We should have already resolved all the labels, so that's also fine. We should get two label indexes, whatever those are. Okay, fine. What is this address? The question is, does this address make sense? And the way we can test this is by going to program memory. Yeah, memory sections, RV code, buffer memory. 3AADD4B, whatever. That is that. And this is exactly the address. I mean, so that makes sense. This is label 0. So the very first thing that we try to put in globals is here. Makes sense to me, I guess. Okay, where are we trying to patch? We are trying to patch at 8. That also makes sense to me. So, I mean, why is that not okay? Why is that not okay? Have this memory. We have it committed. The occupied is wrong. Wait. We should have allocated section memory here. Why is occupied 1? Yep. Okay. Makes sense. The problem is where are we? Here. Right. We are locating in the wrong program. We need to do that in the runtime program. Let's try it again. Right. So let's check again. We have program, memory, sections, RV data, buffer. Okay, that is better. So we have 8 bytes, out of which one is just this character for the character, and then we should have 8 bytes for the actual address. Okay. And we still have access violation. But it's correct. What is the issue here? Memory section. Right. Not enough stars. I think that is the issue. Because this here is not a pointer to S64. It is a void pointer. That's what it is. Is this any better? Page add. So we should have absolute garbage there. and it is still very much unhappy. But now that should be fine. Or is this also incorrect? No, this seems fine. Let's verify again what this does. So it gets the label, and then we have section buffer memory and offset in section. That seems fine. I might want to assert label is resolved. Does that do anything? So we are trying. Actually, no, it is the wrong address. This is address of is 3A66 and yeah, it is totally not correct. Why is it totally not correct? So what's this label? Uh, that does not seem right. Right, this is the same situation. Allocate section memory. Where are you? Right. You have context. Instead of context, we are going to pass you a program so that we can give explicitly a runtime program when we want to. Right. So here, context program, that's easy. Context program. But here it is not context program. In here, we would say program star runtime program is this stuff, and runtime program, runtime program. Again, this and this. Okay, so it's better, but it is totally screwed in terms of alignment. I think that's actually not a problem. I mean, it will still work because it's x86 and x86 can do misaligned reads, but it looks like allocate section memory is a bit busted. Um, maybe? Hmm. I mean, this patch will work. That is okay. The thing is, yeah, I'm not sure about alignment, if that was correct or not. Visual memory buffer, allocate bytes, blah blah blah. Set in section, offset in data. Yeah, that's actually because this is busted. Um, this, I think. Okay, much better. So now we have correctly aligned value in here. The patch actually worked. So now, yeah, we can't look at the patch at anymore, but that's okay. We are running our startup code. Everything is fine. And now the question is, did it work? We go to the assembly. We can now step into the code. This just calls the load of handle. Then we load some stuff into RCX, and RDX is our value here. So if we go to memory, um, right. So this is like this, I believe. Yeah, like this is a dress. It is little endian. That's why this number is sort of reverse of how it is presented here. And here we have our character, and it should point to the right thing, I believe. Let's go to the assembly, and we can verify that that's indeed the case. And here we go. Okay, letter A. Great. So that takes care of the oops, much. That takes care of the JIT version of this. I think I will not actually implement the P32 version on video. If you curious how it will turn out, check in the repository, which is linked in the description in a couple of days. And there should be a commit that will show how this is done for P32. I guess that is all for today. Thank you very much for watching, and hopefully see you next time.